Now let's look at another situation. Here we have a situation where velocity increases from 10 meters per second to 30 meters per second in 4 seconds. The question is, what is the acceleration? Well, the first step we want to take here is to note that if we go from 10 meters to 30 meters per second, we have a 20 meter per second velocity change. Remember that we're looking for acceleration, and acceleration is related to velocity changes. We don't really care what the initial and final velocities are, except that they give us a change in velocity. At least we don't care if all we're trying to find is the acceleration. Okay? So, at this point we know then that we have a 20 meter per second change in velocity in 4 seconds. Well, 20 meters per second in 4 seconds is 5 meters per second per second, because each of these 4 seconds will have to have a 5 meter per second change on the average. So the average acceleration is 5 meters per second per second. Now, looking at the units of the calculation, if we divide the 20 meters per second by the 4 seconds, which is effectively what we did up here, how do the units work out? Well, the 20 over the 4 is going to give us the 5. We'll have meters per second here over seconds. Now, meters per second over seconds, we got meters per second times 1 over second. That's going to be meters over second squared, isn't it? So 5 meters per second squared means 5 meters per second of velocity change per second. These two things mean the same. Now, if we look at the formal way of doing this, we see that in terms of rates, acceleration is a rate of change of velocity. As such, it's going to be the change in velocity divided by the change in time. Now, we note here, and we might want to zoom in a little bit so we can see it better, that this is the definition of acceleration. Okay? The definition of acceleration is time rate of velocity change. And to get the time rate of change of a quantity, you divide the change in that quantity by the time duration. So velocity change over time duration, in this case, is the 20 meter per second velocity change divided by the 4 second time duration, which is a 5 meter per second squared rate. Looking at a picture of a speedometer, we could visualize a 20 meter per second change in the speedometer. This might be our 10 meters per second, this our 30. In any case, this is our 20 meter per second change, and this happens over 4 seconds. If it goes at a constant rate, it's here, 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 and here, and these are our 4 second changes, the change from here to here, here to here, here to here, and here to here. And every second then, on the average, the change will be 5 meters per second. So it's 5 meters per second change per second, 5 meters per second per second, written like this or written like this. Okay, another situation. Going the wrong way here, come back. Let's consider what happens if we have a velocity change of negative 12 meters per second at an average rate of negative 4 meters per second squared. Now, what do we mean by negative velocity change? Well, that simply means a velocity change in the direction opposite to our positive direction. If we're driving in a car, we usually think of our positive direction as the direction in which we're moving. A velocity change opposed to that direction occurs when we stop. Our velocity goes from 60 miles an hour to 0. That's a negative change, isn't it? So we could think of a car slowing down, changing its velocity by negative 4 meters per second at an average rate of negative 4 meters per second squared, which is a pretty fast stop. Not the fastest, but it's a pretty fast stop. You're in a hurry to stop if you accelerate at this rate. In any case, how long does it take you to stop if your velocity change is negative 12 meters per second and your average rate is negative 4 meters per second squared? Okay, well, negative 4 meters per second squared means negative 4 meters per second. So every second of time, on the average, we're changing by negative 4 meters per second. Well, if we want to change by negative 12 and we're changing at negative 4 every second, it's going to take negative 12 fourths second to make that change. And I didn't write down negative 12 fourths of a second is positive 3 seconds. So it's obvious here that it'll take 3 seconds. The calculation would look like this. We have negative 12 meters per second, which is what the negative 12 really stands for here. The negative 4 for the negative 4 meters per second squared. And that's going to give us 12 fourths meter per second, from the meter per second here. And then we're dividing by meter per second squared, so we're going to have to invert that and call that second squared per meter. The second divides into the second squared, leaving us a second, and the meters just divide away. They cancel, so we don't have the meters anymore, and the calculation comes out in the correct units of time, the 3 seconds that we would hope we would get here. The change in velocity, well, looking at the equation, we take the intuitive equation, change of velocity equals average acceleration, which is the average rate of change of velocity, multiplied by delta t, and we rearrange the equation to solve for delta t. We do that easily by dividing by A average. Divide both sides by A average, and we get delta t equals delta v over A average. And then we do the calculation. Well, our delta v is negative 12 meters per second, as stated. Our A average is negative 4 meters per second squared, and as we saw here, the calculation gives us 3 seconds. So we solved an intuitive equation to get a less intuitive equation. This delta t equals delta v over A average isn't real intuitive. Okay? Whereas this one is, if you understand rates. Now, this is the least intuitive form of the equation, the one that's least obvious to anybody with just using common sense. The one check to make sure that we've got the right equation here is the way the units work out. Okay, and if the units work out to seconds for delta t, then there's a good chance that we have the equation right. If the units don't work out, that tells us for sure that we've made an error, the equation's wrong, and we'd better modify what we're doing. Now let's look at a slightly more complex problem, a fairly typical type of problem that we might be able to reason out without resorting to formulas and other witchcraft. And of course we're going to have to do that shortly. Not witchcraft, but formulas. Starting at 10 meters per second, let's say we accelerate at 3 meters per second squared for 8 seconds. What's our final velocity? And what's our net displacement? How far do we travel during this 8 seconds? We can answer both of these questions fairly easily. First of all, our velocity change, well, let's not even look at what I've got in red here. This is all explanation over on the right, but let's just look at what we have. We're changing at 3 meters per second squared, which means 3 meters per second for 8 seconds. So the change is going to be 3 times 8 meters per second, or 24 meters per second. Every second we change by 3 meters per second. In 8 seconds we'll change by 24 meters per second. Then, since we start at 10 meters per second and change by 24, what do we end up at? Well, 34. We add what we started to the change, and we have our final. Now, we want to find how far we go. We want to find our displacement, in fact. How do we find displacement? Well, we multiply the average rate at which position changes by time. The average rate at which position changes is the average velocity. If the acceleration is uniform, which is an implicit assumption here, then our average velocity will be the average of our beginning, 10 meters per second, and our ending, 34 meters per second. Well, if you find the average of 10 and 34, it's 22. 22 is dead halfway between 10 and 34. If you add 10 and 34 and divide by 2, you get 22. So the average velocity is 22 meters per second, and our displacement At 22 meters per second for 8 seconds, what's our displacement going to be? Well, this is the number of meters we go in a second. We're going for 8 seconds. We better multiply it by 22. We get 176 meters. Now, if we want to use equations, and it's always nice to have equations when we need them, though we shouldn't really need them to solve this problem. The equations read like this. We find our velocity change, delta v, which is acceleration times delta t. 3 meters per second squared times 8 seconds gives us our 24 meters per second. Now, there's not a formal equation for this. You could write one. The final velocity is the initial velocity plus a change in velocity. That's real common sense. If you start with something and it changes, then you add the change to what you started with and you get what you end up with. And similarly, the average. If we have the starting and ending, and if we average the two, well, the average of the two is going to give us the average velocity. If we have uniform acceleration, and remember how that relates to the straight line graph and so forth. And then our displacement is our velocity times our delta t, our rate of change of position times our time duration, and that gives us our 176 meters.